Welcome back to Data for SaaS. My name is Josh Hart. I'm a solution architect at AWS, and in this episode, we're going to be covering all things connection management when it comes to relational databases. This is the latest episode in our S.C.A.L.E series, where we cover the scalability, consistency, availability, latency, and evolution concerns that you have to think about when you are building a multi-tenant data architecture. This episode will focus on scalability. That is to say, are we using the compute resources that we have available efficiently, and can we dynamically scale those compute resources as our demand changes over time? In this session, we're going to focus on what is challenging about database connection management, particularly in the context of multi-tenancy, and we'll have a look at the solution using RDS proxy for multi-tenant connection management, and we'll also look at an alternate approach using the RDS data API, and we'll then finish off with a demo showing how to use the RDS data API in a multi-tenant scenario. So let's get right into it. So to begin with, let's think about how the database architecture works. We have the database process. This process then forks, and it creates a new process for each new database connection. So in this case, that could be for each new tenant, we create a new client connection, and that in turn creates a new backend process. This means that for each new connection, each new tenant, we create a new backend process. Each one of those backend processes has an associated amount of memory and CPU that's required just to keep the process alive, just to keep the TCP connection alive, even if it's not actually doing any work. And for that reason, we have a configuration parameter on the database engine that will set what is the maximum number of connections that the database is able to accept. When we hit that number, that means that our application can no longer open any new connections to the database. So as we scale the number of tenants, eventually we'll get to the point where we're not able to open any new connections for our tenants using the application. So to avoid this, the common pattern that we would implement is a connection pool. And we'd have a client-side or application-side connection pool that would allow us to reuse a fixed number of connections in order to prevent the number of connections from continuously growing unbounded. But where that poses a challenge is when we think about cloud compute, one of the core value propositions is that we can scale elastically. So we can scale horizontally the amount of compute that we have in response to changing demand. But as we do that, we're also scaling the number of connection pools that we have. Each new application server we bring online is going to have a new connection pool, and that new connection pool will have a number of new connections that it will try and open. And that means, again, we can be back in the situation where we can hit that max connections setting, and that our newly scaled out application doesn't have the ability to connect to the database. So the pattern here is to implement a centralized connection pooling technology. There's some popular open source and community solutions such as PG Bouncer and PG Pool 2 that can be deployed and act as a central point that your applications connect to, and they then manage the connections to the database process. So let's have a little look at how that works on AWS. So on AWS, when we talk about our centralized connection pooler, we're talking about Amazon RDS proxy. So Amazon RDS proxy sits there as a layer between your application and the database and acts as the guardian that controls the amount of connections that are able to be opened to the database. So this means that the number of connections cannot grow unbounded past the configuration parameter that you specify. And it also means that as the application grows over time, there's a single place that the application connects to in order to request a new connection to the database. And this will allow the application to queue up requests and wait for a connection to become available rather than immediately failing to open a new connection to the database. So let's talk a little bit about RDS proxy and how it works. So it's a fully managed, highly available database proxy that's available for Amazon RDS, Relational Database Service, and Amazon Aurora. And as I mentioned, one of the core values of RDS proxy is that it lets you share connections between transactions using connection multiplexing. So this means that you're able to reuse connections without having to go through the overhead of opening new connections to the database. And it can also reduce the maximum number of connections that your application needs as it scales, because you are able to reuse existing connections and you are able to wait for connections to become available. And this allows you to scale to support hundreds of thousands of database connections without having thousands of connections to the backend database at any one time. So it reduces the amount of resource consumption on the database that is used just for connection management. Now, I mentioned there about connection multiplexing, and this is one of the valuable aspects of RDS proxy, which is that we can use existing idle database connections that have the same configuration in order to run across multiple different clients. So if my client is requesting a connection that has a specific configuration and we already have an existing idle connection that matches that configuration, we are able to reuse that connection without opening a new one to the database, which reduces the amount of overhead on the database and reduces the amount of connections required. Another key feature of RDS proxy is that it can improve failover time. Because the application connects to the proxy rather than directly to the database, this shields the application from any topology changes to the database. For example, if a failover occurs and the standby instance is promoted to be the new primary, the application doesn't have to point at a new connection and wait for a DNS propagation, because it just connects to the proxy, where the transaction will be queued until proxy is able to connect to the new primary instance. And you can think of proxy as being that middle layer. So if you were to split your application into 3 stacks, where you have the application tier and you have the database tier, in the middle you would have your proxy tier. And that proxy tier allows you to provide a security isolation boundary in order to define which applications have access to the proxy, and in turn define access for the proxy to the database. So let's talk now about how we add multi-tenancy into that equation. So when we think about multi-tenancy, we could be talking about silo isolation, we could be talking about bridge isolation, or we could be talking about a pooled isolation. For this example, let's assume that we're talking about a pool isolation. That is where all of our tenants share a single table, and we're using an attribute on that table in order to provide isolation between our different tenants. And that would be our tenant ID attribute. When we do this, one of the controls that we want to implement is row level security. So row level security, we would implement in Postgres, for example, using a policy. And that policy we create specifies which attribute on the table we create the policy for to apply which condition to. So in this example, we're saying on the tenant table, using the tenant ID attribute, where this matches the tenant.id session variable. So that allows us to dynamically apply this policy based on the given session. So that means on the session, we have to set that tenant ID variable, and we'll set that based on some property that we have coming from the tenant authorization context. So perhaps that'll be a claim on the JWT token. When we do that, when we set that session variable, that means that that connection then has that as part of its configuration. And within RDS proxy, what we will do is, if you are setting session variables using row level security policy like this, we'll pin that connection to a client connection. And this means that you get a reduced benefit of multiplexing. The connection isn't able to be reused across different client connections when we have that set variable being used to enforce tenant isolation. There's also another consideration to be mindful of here, which is that within RDS proxy, we're always storing our connection configuration, so our secrets, our username and password, within AWS Secrets Manager. And we're able to store 200 secrets per proxy. So that means if we're using a separate database user for each tenant, that we are only able to store 200 tenant secrets on each proxy before we have to consider sharding and having multiple proxies deployed. And here's an example implementation of what RDS proxy looks like in a multi-tenant application. So here we're again using row-level security to enforce our tenant isolation using those session variables. That means that effectively we're going to get a connection per concurrent tenant or per session variable value. So RDS proxy is still valuable here because RDS proxy is isolating the database from connection storms and allowing us to manage the maximum number of connections that we want to open to the database at any point in time. It also allows us to queue requests so that we don't have an immediate error within the application when there are no connections available. And we also get the failover improvements that were mentioned on a previous slide. There is an alternative to traditional connection management, which is to move away from having a connection-based data access layer. So through the AWS SDK, you can make an API call to the data API service, the RDS data service, and that will encapsulate your SQL statement and send it as a RESTful API call to the service without needing to worry about stateful connection management. It abstracts away the connection management as part of the RDS data implementation. So this means that you don't need any client or application connection pools or any connection pooling logic within your application. You actually don't need any database drivers at all. And you don't need any centralized connection pooler like a PG bouncer or an RDS proxy. Instead, you just use the RDS data API directly like you would any other AWS API call like S3 or DynamoDB, for example. Another interesting feature of the RDS Data API is that it doesn't require direct connectivity to the database. You can run it remotely, and as long as you've got the correct IAM credentials, identity and access management credentials, to perform the execute statement action, then you'll be able to run your query against the database. And this can be really useful in development environments where you want to be able to connect to a development database from your local machine without having to do things like set up VPNs or remotely connect to other machines in order to connect to the database. And this is available with Amazon Aurora provisioned and serverless deployments today. You can see an example of what the code looks like. So this would be your entire data access layer. So rather than having connection management, connection pooling, driver instantiation, any of that logic within your data access layer, instead, you just make a call to the execute statement API, and that encapsulates the SQL that you want to run against your database. So going back to our reference architecture, here is an example of implementing multi-tenancy with the RDS data API. So here we can either enforce our row-level security via SQL functions, or we can do it via explicit transactions, which we'll see in the demo in a moment. But the key part here is that we've removed that middle layer from our architecture. So we've not got any connections to manage, we've not got any centralized connection pooling, or even any client-side connection pooling that we have to contend with here as part of the architecture. So let's take a look at that in action now. So there are two examples of how you can implement row-level security using the data API. The first approach that we're going to look at is using a function. And in this function, we'll set the session variable that's required to provide the tenant isolation. So first of all, I'm going to create my schema. So I'm just going to copy this schema, and then I'm going to paste it into the query editor. Have the data API enabled, we can use the query editor. So here I'm just going to create a table tenant with a tenant ID that is the primary key. And in that, I'm going to insert a record for tenant 1, tenant 2, and tenant 3. I'm then going to create my row level security policy, where we're going to say where the tenant ID is equal to the tenant.id session variable. And then I'm going to enable that policy on my tenant table. So with that successfully ran, what we can now do is we can go back to our script. And because this implementation uses a function to set the session variable, we can take this function now and again copy this across to the query editor to create it on the database. Success. So because this is running as the super user, this means that the row level security policy will not apply. So here, when I'm running get tenant data, even though I'm passing in a tenant ID of 2, I get back the data for all tenants because I'm the super user. When we run this within the application, as the context of the app user, we'll see that the session variable then gets applied and we only get back the data for the correct tenant. So with that set up, we can now run this Python script. And we can see back where we are passing in the tenant ID to. So here we've got it hard coded, but in our actual application, we'd retrieve this from the tenant context, so likely from the JWT token as a claim on the token. And we're then passing that in as a parameter. And then we're passing that parameter set to the RDS data execute statement API call. And that then means that when that function is running, we're then evaluating that session variable at runtime, and we're enforcing our row level security policy. If we're to omit that parameter, then the query will just error. So that means that we always have to supply it. So you can't circumvent the row level security policy by omitting this line from your function. And we can test it now by changing the value. If we say tenant free here, we'll see that we get back the data for tenant free. Now, a lot of this is boilerplate where we've just got the SQL schema defined for convenience. If we remove that, really see how succinct this code becomes. So where you might normally have drivers and connection management, connection pooling logic within the application, instead, this Python code looks similar to where you might have other AWS SDK calls, things like S3 buckets, DynamoDB tables. So for things like Lambda functions, it can make your deployment package and your overall data access layer much more succinct. Let's take a look at a second example now. So whereas the previous example used functions, so it required you to define the session variable as part of your SQL schema, here we're instead going to use an explicit transaction. The RDS Data API supports transactions, and those transactions mean that the statement will always run against the same connection. So that means that even though we're running separate statements, we can guarantee by using an explicit transaction that they're always going to run on the same connection. And that means that we can set our session variable, and then we can run our query, and the session variable will still be evaluated and used correctly. So if we take a look at the code here, we can see that we are beginning our transaction. We're then running an execute statement that sets the session variable, and we're then running another execute statement that selects the tenant ID from the tenant, same as in the previous query. And in both of these, we're passing in that transaction ID, so we're in the scope of that explicit transaction, and then we commit the transaction at the end. So this code is slightly more verbose, but it means that you don't have to incorporate any specific additional logic within your SQL schema. So let's see this one in action now. And there we can see again, we've got back just the data for tenant 2. And if I change this to tenant 3, you can see back that we only get the data for tenant 3.
And again, just to prove that this is a safe mechanism, what we can show is that if this session variable isn't set, that we're just going to get an error. So we can see here in this situation that because there is no session variable available, that we are unable to execute this query because the row level security policy can't evaluate successfully. So that prevents us from a developer misconfiguration, from omitting this line of code, either in this implementation or in the function-based implementation. So this always has to exist somewhere. So it means that we have an extra layer of defense when it comes to implementing our tenant isolation. One of the other benefits here is that I'm running this from my local machine. So I don't need to have direct network connectivity to the database in order to run my SQL statements. I'm able to run this, and because I've got IAM permissions set up locally as part of my SDK, I'm able to run these execute statement commands against the Aurora database that is existing securely within its VPC without having to expose that over the internet via a VPN or some other means, which is powerful for local development scenarios, but also for serverless applications such as AWS Lambda, where we're able to connect to the database without having direct network connectivity.
Okay, so let's have a quick recap. So it's important to consider connection management as part of your scaling strategy. In an earlier session, we covered horizontal and vertical scaling as two of the core pillars of your relational database scaling strategy, and connection management is very much that third pillar. And it's often overlooked as a significant contributor to the performance and overall health of your database. So as such, you have to know what the limits of your database are. What is the maximum number of connections that you can support concurrently? And what's going to happen? What's your plan as you grow to approach that limit over time? For multi-tenant applications, that means thinking about when you have varying levels of tenant activity, when you have a sudden spike in tenant activity, how do you manage that from a connection management perspective? And that'll mean you want to think about one of two options. You want to either adopt a centralized connection management tooling, such as RDS proxy, so that in your auto-scaling compute environment, the database doesn't become the bottleneck and you're able to scale as your application grows. And the other option is to consider moving away from stateful connection management and instead move your entire data access layer to use the AWS Data API via the AWS SDKs. So thank you very much for watching. I hope you found this episode interesting, and we look forward to seeing you in a future session.